Today, the objective is to be able to sketch graphs of functions using transformations. So they start the section just giving you a visual of 6 really common parent functions. And of course there's others, but these are the 6 that we tend to use a lot when we explore the idea of transformations. So make sure you know these functions, you recognize it, you understand when you have these particular types of functions that they will produce these basic general shapes of graphs. Now this section breaks down the different types of transformations as follows. On page 99 they talk about vertical and horizontal shifts. Those are what we call rigid transformations because you move the graph without changing the size or shape of the graph. Then they go on to talk about reflections. Again, when you reflect a graph, it doesn't change the shape of the graph, it just changes the orientation of the graph. But then they talk about non-rigid transformations on page 102, and those are stretches and compressions. Those do change the shape of the graph. Not the nature of the graph, but it changes kind of how quickly it rises or stretches out and so forth. But the way that I like to kind of give an overview of this section is to say that there are 2 basic principles when it comes to transformations that, if you fully understand, will help you to graph any function. And so here they are. You will not see this in your textbook expressed the way that I do. So take it or leave it if you think it's helpful. Otherwise, you could just stick to the exact methodology of the textbook. So basic principles of graphing with transformations. So I have 2 basic principles that you need to understand. First, all transformations that apply vertically, vertical transformations, are always direct. So if it says to add 2, you go up 2. If it says to subtract 2, you go down 2. If it says multiply by 2, then you're going to stretch it by 2, and so on. Whereas horizontal transformations are always the inverse of what they appear. So if you have an x plus 2 inside the parentheses, instead of going to the right, which is what you would associate with the plus, you go to the left. And then if it has a 2 times x inside the parentheses, instead of multiplying the x values by 2, you're gonna multiply by 1/2 or divide by 2. So that's the first basic principle. Vertical transformations are direct, horizontal transformations are inverse. The second basic principle is all transformations that happen outside of the parent function are going to be vertical transformations, whereas any changes that happen inside of the function affects the horizontal component of the graph. So those are my basic principles, and now we're going to look at some examples. So in this one, they want us to graph a cubic function -1. So what does the -1 do? Well, the -1, notice that it's happening outside of the cubing function. So that immediately should tell you that it's going to affect the vertical component of the graph. Now, vertical components are always direct. So because it says to subtract 1, you are going to subtract 1, which means that vertically, this thing is going to shift down 1 unit. Okay, so if we consider 3 basic points of y equals x cubed, and I'll just use these values. So you'll see now that if you move everything down 1 unit, all the y values will now subtract 1. So this will become -2, -1, and 0. And of course, the x values will stay the same because we didn't do anything to the x values. So this chart now is the xy chart for this function. So let's graph it. So -1, -2, 0, -1 is the middle of the graph, and then 1, 0. So cubic functions look like this. And voila, there you go. Okay, now let's look at b. b is another cubic function, but this time you got a little bit more going on. Again, the +1 is happening outside of the function, so it's vertical, and that's going to move everything up 1 unit. The +2 is inside of the cubing function, so this is going to affect the graph horizontally, and horizontally it's going to do the inverse of what it appears. So rather than add 2 to the x values, we're going to subtract 2, which is going to move things to the left. Okay, so again, thinking about our regular y equals x cubed, normal y equals x cubed points are these, but we're going to add 1 to the y values, so this will be 0, 1, 2, and we're going to subtract 2 from the x values, so it's going to be -3, -2, and -1. So these are the points we're going to use for a quick sketch of this. So -3, 0, 1, 2. Okay, so -3, 0 is here, -2, 1 is our middle, and -1, 2 is here. So our cubic graph looks something like that. Okay, now let's look at some reflections. This time they don't actually want us to graph it, they just want us to compare how these graphs would look to the original parent function f of x equals radical x. So we see that we have a negative. This negative is occurring outside of the radical function. Outside is vertical, so therefore this is going to flip the graph vertically. Now, just really quick for a visual, if f of x is radical x, this graph, square root graph, looks like this. So if you flip it vertically, it's going to flip over the x-axis, and it's going to look like that, okay? Okay, so anyways, this is going to be a reflection, therefore, if you flip it vertically, it's a reflection on the x-axis. Okay, the second one, however, has a negative inside affecting the x directly. So this is going to cause a horizontal reflection. Horizontal reflection means you're flipping it over the y-axis, so it's going to end up looking like that. Okay, oops. So that means it's a reflection on the y-axis. And then finally over here, you've got the negative outside, so we already determined that that's a reflection on the x-axis. And then we also have this +2 inside, so that means that the graph is going to shift 2 units to the left. Okay, so basically what that's going to do is if you shift it 2 to the left, maybe it starts here, and it's flipped, so it's going to go down this way. Okay, or you could flip it first and then shift it 2 to the left. All right. So finally, we look at non-rigid transformations. So these are your stretches and your shrinks. We have a basic parent function of absolute value, which hopefully you know is this v, absolute value of x. Okay, so we're looking at a function that has a 3 in front, multiplying. So you're multiplying the function times 3. It's outside, which means it's vertical, and it's direct. So it's going to multiply all of our y values by 3, which in effect is going to cause a vertical stretch by a factor of 3. Okay, so that's going to make it skinnier because all the y values are going to increase 3 times as fast. So it's going to be a skinnier graph. Okay, the other one, 1/3. So again, it's outside of the absolute value, and you're multiplying the y values by 1/3. So if you multiply the y values of 1/3, they're going to increase slower. Oops, why did I write stretch? So therefore it's going to be a vertical compression or shrink by a factor of 1/3. So it's going to make it increase slower, which is going to make it look wider. Okay, so I think if you follow the basic principles, you shouldn't have a problem. You do have to be familiar with the basic graphs. And let's just do one more, example 4. So now we're comparing graphs to our original graph they're giving us as 2 minus x cubed. Okay, so they want us to know what happens if you do f of 2x. Sorry about that. Zero period is about to start. Okay, so basically this new function g is going to be the same as f, except your input values have a 2 inside with the x. So if you were to replace x with 2x, it's going to cause a horizontal, and because horizontal transformations are inverse of what they appear, instead of multiplying by 2, you're going to multiply by a half. So if you multiply your x values by a half, it's going to be a horizontal compression by a factor of a half. Whereas for b, if your new function is the f function where your inputs are halved, sorry again, so if your inputs are halved, horizontally something's going to happen because it's inside. It's the inverse of a half, which is 2, so you're going to multiply the x values by 2, which is going to cause a horizontal stretch by 2. Okay, that's it. We will practice this more in class and hopefully master it.